Good morning to everybody. Welcome here at the EIC Summit. Happy to join with you, hopefully the interesting next 45 minutes. Thanks to all the colleagues that organized together with us this session. And now in 2 minutes, I will try to describe what hopefully will be the next interesting session. As I was saying, we, Marco and me, are the two program managers of EIC on green technologies. And here, what we would like you to join is a 45 minutes discussion with experts coming from science as well, from VCs and from innovation fund projects. We will discuss later who are the hosts and the guests, and scientists from funded projects to show you what does it mean when we say that EIC is an hands-on agency. It means we are an agency of European Commission that has got the ambition to help in overcoming the European paradox. And how do we do this? We are something like a startup managing a lot of money, but we want to give this money to the best innovators. We want to create the culture of helping the innovation journeys of all the type of researches going from the low TRL, from the medium TRL, and from the high TRL. So going from research project to innovation projects, we look for developing these kind of things with what we call proactive or hands-on management. What does it mean? It means that the group of EIC, where we are part, the program officers, we work with the colleagues content-wise with the projects. It means we try to work with the projects, trying to help them, nurturing their needs, discussing with different type of stakeholders, both science-wise and technologies-wise. And so today we are here with the business part, with the science part, to show you how we normally try to help, try to stimulate the strategic intelligence side of the business and innovation journeys. So coming from the idea in the lab, going to the market. And today we will do this thanks to the wonderful discussion, hopefully. And now I give the floor to Marco that will describe the topic of today's session.
Thank you, Francesco. Thank you, everybody, for being here with us. And yes, we selected this topic on hydrogen, which is a key piece of the broader puzzle to enable the decarbonization of the energy system, but also of the industrial sector and all the carbon footprint of our planet. But as Francesco said, we also would like to present our vision about the sustainable development of innovation at European level, which means to add key aspects of the hydrogen innovation journey, such as the use of non-critical raw materials and looking at the whole sustainability along the whole value chain of the production of each component of the hydrogen conversion process, but also looking at the integration of hydrogen within the broader picture, and in particular using it in sectors where the benefits can be maximized. Heavy transport, hard-to-abate industrial sector, mixing the use of hydrogen with the carbon capture to produce renewable fuels, and addressing the specific topic of transport and storage of hydrogen, with in view in mind the key challenges to minimize the environmental impact, to guarantee the European autonomy with the supply chain of the raw products, raw materials that are needed for these processes, and looking at how where better use this hydrogen and how to integrate the storage within the whole process. For this reason, we have now and we will introduce the first speakers. Francesco, may you want to give the floor to them?
We give the floor to we funded recently this project that started a few weeks ago. The name of the project is LESGO. I introduce here Carles Ros that will introduce his project in 5 minutes, and then we give the floor to the next speaker. Thank you, Carles. The floor is yours.
Thank you very much. if I can see the slides, sorry. Hello, everybody. Thank you very much for inviting our project here to be shown in front of all the EIC. Our project is a LESGO project. We come from the Catalan Institute for Photonic Sciences in Barcelona. Our goal of our project is to store hydrogen bonded to graphene oxide. Graphene oxide is a carbon derivative, as you know. And the idea of the project is to be capable to store this material in solution in water, so we are capable to have a fuel which can have the hydrogen stored in it, so we can store and recover the material. I'd like to see the slides if it's possible for everybody to follow up. Okay, thank you very much. This went too far. Yeah, this is the project. The LESGO project is the one I'm presenting today. So the idea I was saying to hydrogenate the graphene oxide so we are capable to store the hydrogen there and then to recover it back on demand. The idea we want to face is that we need the possibility to fast fuel automobiles, fast fuel the trucks. Also, we need long-term storage, a fuel that's capable to be stored for long periods and not losing part of its hydrogen during the time. Also, we want to face this problem using materials which are not toxic, safe, they are earth abundant. And the fuel we are proposing in LESGO, and we're working now, it's a liquid fuel. It's non-toxic, and it's also safe. It's water-based, so it cannot burn, it cannot freeze by cryogenic temperatures, and it's also based on carbon and water, so it's earth abundant. As you can see in the picture in the right, we are storing this hydrogen directly bonded to the graphene structure. The idea of our project, our solution we are proposing, is to, in a single step, convert water and graphene oxide coupled with photovoltaic technology, in this case, but could be also wind technology or other renewable technologies, and in a direct step, convert it into a hydrogen-rich fuel, as a black color, as you can see here. This material can store the hydrogen for very long term, and it's in water conditions, so it's easy to store and to manipulate to fast fuel the trucks. It's non-toxic, everything is done in liquid conditions. It's easily upscalable because we are using technologies like electrolyzers and fuel cells, which are already available for the high-developed technologies. And I was saying it's a long-term storage possibilities. Our team, which is involved in the LESGO project, it's including 6 research centers all across Europe, but also 4 industrial partners which have joined the project in the value chain that you can see in this graph. We have a partner who's capable to convert the graphite into the graphene oxide, the raw material that we use for the project. There are other partners which we are also interested in showing us, because other partners could at some point be interested in the technology, which involve into converting water by water splitting into the electrolysis and storing this hydrogen in the graphene oxide. Other partners related to recovering the hydrogen from the graphene oxide, so into releasing by fuel cell technology this hydrogen and converting back to electricity on demand, and finally on testing these fuel cell vehicles in the real world conditions. No? From stakeholders, we have identified 3 different potential markets: fast fueling of heavy transports like trucks, to be capable to use as a gasoline, easy fueling, not as batteries that really need relatively long times to recover and to recharge. For example, also maritime transportation, or seasonal or daily storage to be capable to store the energy surplus that we have from some renewable energies in electricity into this fuel to be recovered during, for example, night. Right now, we are facing the TRL increase to improve the technology, upscale it, validate it in different conditions. We are searching for financial support, both for prototyping and also for the research part, which is important in a low TRL technology like is ours, and also into explaining to society, like we're doing today, our approach, the possibilities, its low carbon cycle consequences, and also to everything related to certification of this fuel. And as you can see in the graph on the right, the main bottleneck we have is the important part of the project, the catalysis into storing the hydrogen in the graphene oxide. Because all the other phases that this project includes, it's mainly already developed in high TRL technologies. You can see it more or less here as we propose in this timeline. The idea of the project has been facing this LESGO fuel catalysis into converting the water into hydrogen stored in the graphene oxide. And because further steps could be really fast, because many of the involved technologies, like the fabricating graphene, electrolyzers, fuel cells, photovoltaic or electric vehicles, are already quite close to the market. So our project, if it's successful, with the help of all the research and the partners involved, could do a significant fast change if it's accomplished. So thank you very much for listening to us. Here you have the contact for us if you need further questions. I will be here during the Congress for the whole day, so you can find us for whatever you need. Thank you very much.
Thank you very much, Carlos. This is a very good example of a Pathfinder project with breakthrough fundamental research to explore new pathways for innovation. But at DIC, we have the ambition to cover the whole innovation journey. For this reason, we have invited to this session also an ESC accelerator project at more advanced level in terms of technology, and also market deployment of the similar approach in terms of innovative hydrogen storage, but with liquid organic carrier, so quite different technology, but to address the same challenge. So I'll give the floor now to Belén Moreno from HySiLabs that will present the project HYDROSIL, winner of a ESC accelerator grant. Probably Belén is online and should be available to present. Hi, I see you now.
Hi.
Hi,
Good
Belén.
afternoon, everyone.
So, welcome, and please, can you tell us what is the key novelty that you are proposing, and why your project is so interesting, and the floor is yours. Thanks.
Sure. Thank you. So HySiLabs has actually developed a liquid carrier to transport and store hydrogen, and we are based in southern France, and we were we won the EIC accelerator in 2020. So in the middle of COVID crisis, which was actually a gift during this rough time. So HySiLabs is a company that was founded in 2015 thanks to a breakthrough innovation of releasing hydrogen from a silicon hydride via spontaneous reaction that does not actually require any energy input. Because, well, as we all know, hydrogen will help us finish with fossil fuels and reduce the carbon print we have today, as it only rejects water when we extract the energy from it. But today, the current ways of transporting it have either a very high pressure or very low temperature. Well, any technical constraints that make these technologies expensive, or directly we don't have the infrastructure we will need, which is the case, for example, for cryogenic hydrogen. And also, of course, if we want this hydrogen to be green, we need to link its production to places where renewable energy is available and it's cheaper than other places in which we don't have this lack. In this context, the molecule hydrogen was born. Thanks to it, we can actually envisage a new massive logistics change. This new logistics change that was never thought of for hydrogen is now possible thanks to HYDROSIL, which is our molecule. HySiLabs solutions will enable hydrogen transportation and storage thanks to it. But how are we going to do it? Well, via this unique liquid inorganic hydrogen carrier. As far as we know, it's the only inorganic hydrogen carrier in liquid state that is known. And this molecule is actually liquid, stable, and safe at ambient temperature and pressure, which is different for any other way of transporting or storing hydrogen today. Plus, it's also non-toxic and eco-friendly, which makes it safe for the planet. And not only can we use the existing infrastructure, such as, for example, all the infrastructure for hydrocarbons that shall stay free, but also we can reduce up to 40% of GHG emissions with it. and up to 50% of money savings compared to other hydrogen transportation solutions. Also, it has an 8.7% of hydrogen density in it, which is actually 7 times more the density of hydrogen in compressed gas, in compressed gas. Plus, also the release of the hydrogen from the molecule is spontaneous. That means that we don't need any energy input needed, and this is so unique to our liquid carrier. Any other liquid carrier would need an energy input to release this hydrogen. Our solution is definitely ideal for green hydrogen market. This is our vision. We always envisioned a molecule that would fit on the green hydrogen market. And because of its properties, we identified 4 main markets that represent 21 billion euros in 2026. And this is the selection that actually fits with the characteristics I just explained. But let's see why we say we are 50% up to 50% less expensive in a practical case. As you can see, these are 3 use cases that regroup different distances and there is technologies to transport hydrogen for these distances via different types of cargo, either by boat, either by road. And in any of them, HYDROSIL is the best technology that we can use for either a huge distance or not as big distance as we could imagine, for example, from the south of Portugal to the north of France. Because indeed, well, since we actually patented our molecule, we took the long way. We took a lot of time to develop this. Nothing in literature was known before. So today, thanks to the EIC Accelerator, we are about to start our Series 8 fundraising in 2022, because the EIC Accelerator founded the demonstrator of a 6 to 7 TRLs of our solution. And this fundraising will be taking place next year. We are very happy about it because, since we started in 2018, the first milestone that we are going to have is right now this large-scale demonstrator we are building, and we will further do other fundraisers in 2025 and 28 to go industrial and to dominate the industry of hydrogen transportation. Of course, we wouldn't be here today without the amazing talents we have in our team that develop around 60 patents of HySiLabs. They are all ours, and they regroup not only the HYDROSIL molecule, but also the process of charging and release. That's why we are kind of the first in the world of liquid inorganic hydrogen carrier. If we all wonder the carbon future thanks to hydrogen, we need to think of HySiLabs solutions as the enabler of this game changer. Thank you very much, and I guess you will have plenty of questions, so do not hesitate to come to me and ask this. Thank you.
Thank you very much, Belén. Let's clap our hands for the very interesting presentation. And now, as we say in Italy, we serve the meal, and now we start discussing and eating. So we give the floor, if possible, to Professor Chen. Are you in, Ping? Can you hear us?
Yes, I can hear.
Okay. Can you kindly, Ping, introduce yourself in 1 minute? And then the floor is yours to make questions to LESGO or to HYDROSIL or HySiLabs, so whatever you prefer. The floor is yours, Ping. Thank you.
Thank you. Hi, I'm Ping Chen from Dalian Institute of Chemical Physics, Chinese Academy of Sciences. And I and Marcello, we have been in hydrogen storage for many years. And we have also, with IEA Hydrogen Task, we work together. So it's very nice to join this events. For me, it's very interesting to hear these 2 presentations. One is for graphene oxide-based material. So my first question to Thales. And I'm wondering that for this, for your system, is hydrogen release you need energy input or just a spontaneous hydrogen release from your material? As I can see from your presentation that during the reaction of your graphene oxide with water, you create carbon-hydrogen bond. So that means that your hydrogen is chemically stored in your material. Am I correct?
Sorry, can you repeat the last question, please?
Yeah.
Your last sentence.
That, yes. Wondering that it's hydrogen stored in your material in a chemical way.
Is the hydrogen, Carlos, stored in the chemical way or in the physical way? Is it absorbed or adsorbed?
Chemical absorption, yeah. We are bonding literally the hydrogen to the carbon.
And my also question is there, when you release hydrogen from your material, do you need temperature or do you need catalyst? How fast hydrogen can be released?
So, yeah, this is a good question. This is precisely what we are researching right now. As we were saying, this is a project we just started 1 year ago from a very incipient idea there was. Right now, we can desorb this hydrogen easily with temperature. We need results about 300, 400 Celsius degrees. But the idea is that this is a first step to understand the dynamics of the chemical desorption from our material. The idea further on is to start introducing catalysts which can lower this kinetic or this thermodynamic barrier, so we are capable to desorb with much less energy, up to the point that the idea is that this material doesn't require temperature. It can be done directly in water environment and in fuel cell conditions. So the intention is that this material can, as a liquid, touch any kind of membrane, which is fuel cell membranes, and be capable to give this hydrogen to the membrane and close the cycle, the circuit as electricity, and this way generate electricity directly from the liquid.
Thank you. And then I have another question to Belén on silicon sealant-based material. It's very interesting that you mentioned that this is a very first inorganic solution for the hydrogen storage. So my question is that compared with the sodium borohydride solution, the water, we know that sodium borohydride will hydrolyze to hydrogen. This is a known technique. So compare with that technique, what's the advantage of your system?
Well, thank you for your question. Compared to other solutions, such as, for example, the one you mentioned, is the fact that our density is one of the highest one compared to other hydrogen carriers. It's 8.7%. I don't know for sure the percentage of hydrogen density in sodium borohydride, but I'm aware that it's a little lower. And also the fact that we can actually transport our molecule with existing infrastructures. We can actually, at the moment that we bound the hydrogen into the silicon, we create the silicon hydride that you can transport with the existing infrastructure. So we won't need to do any investment on that. And the most important part is the fact that when we are going to release this hydrogen, it's going to be an spontaneous exothermal reaction. So we won't need any energy input. That's the main difference. That's the main innovation. And the three of them make HYDROSIL the game changer it is.
Yeah, it's a very good point there. But if maybe you know also that sodium borohydride also give hydrogen spontaneously. This hydrolysis is also an energy-free with a spontaneous reaction. So my question is that if you release hydrogen from your system, you need to regenerate your material back to the hydrogen-rich state. So what's the energy requirement? Do you know can you give us an estimation on the energy requirement for the regeneration of your material?
Sure. So indeed, we are going to recycle this material. We are going to transport it back to the point of what we call the charging point. And at the charging point, we are going to need more or less the same energy we used the first time to charge hydrogen into it, because the process is so industrial intensive. It's going to use anytime 40 kilowatt hours per kilogram of hydrogen.
Thank you. So, Francesco, my question is fun. Thanks a lot.
Thank you very much, Chen. And coming back to the overarching aim to use hydrogen where best fits, where we can maximize the environmental and sustainability aspect. I believe that hydrogen can be used in heavy transport, in aviation, in shipping, in areas where really we don't have an electrification alternative. For this purpose, it's particularly interesting to see what kind of storage technologies could also look at this potential integration and to maximize the use of hydrogen where we really need alternatives and we don't have other options. So now it's a true pleasure for me to leave the floor to Professor Baricco. Marcello, could you please introduce yourself and then tell us a bit more about your experience in hydrogen storage and in particular in metal hydrates, where you've been working since a long time, and how you see these technologies with liquid carriers, powders in the overall research and innovation arena. And of course, if you have hot key questions for our projects, they are more than welcome. Please, Marcello.
Yes, thank you very much indeed. It is a pleasure for me to join this meeting. My name is Marcello Baricco from the University of Turin. As you said, I'm playing with metal hydride since a long time. And together with Ping Chen, we are in the International Energy Agency Task 40. As you said, I'm playing with the metal hydride since a long time. And frankly speaking, liquid is a dream for the people working in hydrogen storage. So in some sense, hearing about liquid state is a pleasure for us because this has been a discussion for a long time in the past. But because I have just 6 minutes to my time, so let me point 6 topics. The first one is, as you said at the beginning, we have to play with high TRLs. So the key point is how these technologies can be really moved to the high TRLs. And the point is, when we are talking about hydrogen, we are talking about quantity and quality. And when I'm talking about quantity, I'm talking about kilos and in some cases up to tons. So the first point is how much this technology can go into the direction of tons of hydrogen. The second point is related to what Ping was already saying, related to the thermodynamic of the system. As you say, the reactors have a spontaneous reaction in one direction, but it has to be not spontaneous on the other direction. So that is a point that has to be clarified when we are dealing with new technologies. The other point is related to the kinetics. As Pinch was saying, we need a fast delivering of hydrogen, either in uploading and in downloading. So you are talking about catalysts, you are talking about silicon. One point is to understand how much these 2 different steps in your technologies are related to the critical raw material. Silicon became a CRM when it is at electronic grade. So it is crucial to understand what is the purity of the silicon that you need, because this can have a high impact, in the upscaling. And we are dealing with catalysts that, to my understanding, you don't have yet in your hands. You have to take care of the presence of possible critical raw material. The fourth point is if the technology is able to take any hydrogen, because we know that right now we have hydrogen coming from the electrolysis, but we have also gray hydrogen that is running around. So how much the technology is sensitive to the quality of the hydrogen and the pressure of the income hydrogen in order to be able to say this is a spread technology for any kind of applications. The last point is related to the applications. We see in the LESGO project that there are partners from industries By the way, two of those partners are nearby me, so I know the system and then the companies very well. So I just like to stress the point that in such a kind of project, demonstration have to be clarified, shown. So it is crucial to understand how much this, let me say, starting point can actually be applied in the real demonstrator. And when the demonstrator are looking for hydrogen handling, they ask basically 2 points. The first is cost, and the second one is, in some sense, density. You mentioned in your websites that you are dealing with 10 times density of gaseous in one case, 7 times gaseous in the other case. So these numbers on density have to be clarified in order to attract potential investor in one sense and the applicants. That's it. Thank you very much.
Many thanks, quite a lot, but...
Yeah, we noted all the parts. As we can say, Marcello, we always see that you are a full professor, so we were listening. Carlos took all the notes. I also took the note, Carlos, so if you lose something... Belén, I hope you take all the notes. It's in my notebook anyway.
I did. I did indeed.
No. Thank you very much for the questions. They are really the key questions that the project right now is trying to face. No? We have some partners which are experts in understanding the field of the market that we have to precisely respond to, which are the questions you were giving us. No? Quantity and quality, at least we're working with raw materials, and if they are pure from their origin, so it's not a part of our project at least, but carbon, and pure water, our product will be abundant and purely carbon and hydrogen stored in it. When we release this hydrogen, our intention is this hydrogen is pure because the carbon is a part of graphene, which is quite a strong material, so we don't expect to generate hydrocarbons together when releasing the hydrogen. You spoke also about the velocity during the process, no? Both the velocity on releasing the hydrogen from the material. We expect to do this fast, but we don't really know because we really have to work a lot on the scientific part to understand the dynamics, but here was the catalyst play a role. I will talk about the catalyst later. And, but at least we have a liquid hydrogen storage, so we intend to be fast on charging the vehicles, the long storage, whatever we do in flow cell conditions, for generating in flow cell conditions or for fueling a car, like in a actual infrastructure of fueling cars or distributing energy. No? Scarcity of materials. We are facing right now only water and carbon, so these are very abundant and cheap. But the catalyst I spoke about, yeah, it's the key role that will play a key role in the fabrication. They will develop complexity in fabricating the graphene oxide, including this catalyst atomistic incorporation in the nanoscale of the material, so to reduce both the energy balance to be releasing this hydrogen together with also the speed of this release, because it's a kinetic part of the chemical bonding. You spoke about how pure do we need this hydrogen when we store it. The good part of our project is that we are not storing hydrogen. We are generating directly from water, graphene, and the renewable energy in electricity. We are directly generating a fuel containing hydrogen. So it's as pure as the water and the carbon we inserted, but we do not require a purity on the hydrogen feed that it's given to us, because we are generating our own hydrogen from breaking the water molecule, together with a bit of hydrogen gas and oxygen, which is a side product that could be used for other purposes. And yeah, you spoke about the demonstrators, the cost, and two critical parameters, the gravimetric density and the volumetric density. These are the key parameters, because right now hydrogen as a gas has a main problem. No? It's a very energy-dense material, but it's a small molecule which occupies a lot of volume, and we cannot have cars with a very large tank, because then there's no space for the car. Or lithium batteries are very heavy for storing the energy. No? So for long travels, we need a lot of batteries. There's a lot of weight in the cars, which we will have to move. Yes, this is the scale of the project that precisely the project will try to face. We are expecting to beat the hydrogen gas and cryogenic hydrogen with our project, but this is a question that will be answered during the development of this project. And so for that, there are partners, experts in trying to find the key parameters for that. But also, well, here we are to expose our project. So if anybody wants to give any contribution, we are open to that.
Yeah, thanks, Carlos, for your very comprehensive reply. I will leave also the possibility to reply to Belén before coming back to some other issues related to the innovation market and so on. But please, Belén, and then we go.
Okay, so
I ask you to be a bit quick. Sorry.
Questions. Yeah. Luckily, I also noted the questions, so I will try to answer as fast as possible. So regarding the quantity of hydrogen, of course, if we are determined to go industrial, well, we never thought of HYDROSIL to be used for small quantities and low qualities. HYDROSIL has been a molecule that has been optimized for have the best quality, and in terms of quantity, we are actually open to the best quantities we could actually think of for transporting hydrogen via HYDROSIL are up to 10 kilotons. That means that we are definitely ready for massive transporting massive quantities of hydrogen. Regarding the quality of raw materials, well, and the silicon is actually it's going to become it's going to be born from silica, any type of silica. We are going to modify silica of any type of quality, and it's going to be the carrier, a perfect carrier that can actually carry any type of hydrogen. That means that even if we have hydrogen, gray hydrogen, any type, or even if we have dirty hydrogen, that means hydrogen with impurities, this hydrogen is going to be purified during the process, and at the moment of the release, we are going to only release the purest hydrogen, almost 100% pure hydrogen, which is actually perfect for example, fuel cells. About the kinetics and the spontaneous reaction, well, it takes around a few seconds to release the hydrogen. Of course, it will depend on the quantity we want to release in and the time we want to. But the only thing that will change is the quantity of thermal energy that we are going to generate from this process. But in a few seconds, we can actually release the hydrogen we have into our HYDROSIL. Also, regarding the applications, well, this actually is going to also answer the fact, the question of density, because, for example, one of the applications we have in mind is the underground strategic storage. The underground strategic storage is something that is done, that has been envisaged to be done via compressed gas, but it can't, because it takes a lot of place, a lot of room, and it's kind of complicated to keep it in gaseous state with no technical constraints. In our case, HYDROSIL is perfect for that because it's a liquid that we can isolate in underground storage and underground caves, and there won't be any dangerosity because hydrogen won't release by itself. And regarding, of course, cost, cost is the obvious question. In any case, we did the technical assessments and the economical assessments to be able to say that the ideal price that we will get once we will get industrialized will be around 3 to 4 euros of hydrogen produced and stored into HYDROSIL. That means that in the end, we will be able to bring hydrogen from places where it's cheap to produce, for example, where we have renewable energies, to places where it's expensive at around 3 to 4 euros delivered.
Thank you very much, Belén. And now we move from the science questions to the market and financial questions. So it's a pleasure to have Kinga Stanisławska and Alessandro Zampieri. Kinga is working in the VC world, and Alessandro is working more on the Breakthrough Energy Initiative in the part of the project. So I give the floor to Kinga to make questions and introduce herself. Thank you, Kinga.
Thank you very much, Francesco. Great to be here. Kinga Stanisławska. I am an IC member of EIC Fund, and I am also working in the venture capital space for a number of years. What I wanted to ask, perhaps starting with the more advanced company, so Belén, what is the final vision for this company? What it is that it's dreaming about? Where will it go? And then the same question to you guys, although I know that you're still early in that roadmap, but always founders see that. So would love to just understand, about your vision.
Thank you for your question. So, the final vision, the one we want to accomplish in 2028, is to be hydrogen providers, because hydrosil is a molecule that doesn't exist per se. It needs hydrogen to exist. That means that if we deliver hydrosil, we are delivering hydrogen. In that case, when we count on making sure that 80% of the value chain of hydrogen is going to work, that means doing key partnerships with hydrogen producers, logistic companies, etc., and delivering hydrogen through these end users of hydrogen that will use either for mobility, for in the industry, for different applications, the hydrogen.
Now the floor to you, Carlos or Luis.
I'll answer. Well, just to say that I'm in the LESGO project. I am representing the knowledge and technology transfer of it. And in regard to your question, Kinga, I think the point is that we try to represent the consortium as a whole, and we want to establish a solid IP portfolio that would enable not only the final LESGO application to develop, but also if individually each of the members of the consortium can find an end application and exploit these patents, that would be an added value to the whole project. But eventually, if we try to focus on hydrogen and LESGO as a hydrogen carrier, we expect to apply to further funding, even provided by the EIC or any other funding. And this is really why we are in this place. We are open to all the discussions, to all the criticism, and try to see where the technology can develop, and what is the trend in the market, and what is the trend in funding. This we need to know just to see where the next 3 years will take us.
Okay, both of your companies are looking in terms of HySiLabs. It was already in the presentation, but both of your companies are looking ultimately for financing from either corporates or from the venture capital market, angel investors and other institutions. And in terms of that, in addition to money is important. What is it that you're expecting to get from your investors? What kind of smartness do you think could add to what you have to build the company together and to have success? Maybe starting with you guys here.
No, yeah, that's really also another very important factor, because as scientists, we are used to maybe focusing only on the science, and bringing this into the market requires a completely different mind and a complete different set of skills. So I think when you have investors working along your side, interested in your project, understanding your technology, you really learn much more from them than from the scientists, because you're not concerned anymore with the science. We're concerned about selling the technology and really getting into the market. So the ideal contribution or collaboration with VCs or other type of investors would be to them working along you, understanding your technology, and this way learn how to develop it and sell it. This is basic for us researchers that sometimes don't understand or don't know how to communicate correctly to the investor world.
And if I can add a little thing, as a scientific in this part, it's very usual to see that the scientific wants to get deeper and deeper and deeper into the knowledge, and somebody has at some point to put a stop or to redirect the direction. What is less costly? So let's try to first search for catalysts which are less costly. Let's aim for materials which are less costly. This approach, sometimes the scientist doesn't spend too much time in researching where really the cost is an amount of knowledge which somebody has to learn on that. We have learned as scientists how to do the thing, but maybe not in which context completely to do that. So it's very important always to not just do science by science, to do science to transform the society, to transform the world, because we are facing some problems as a society that we really need to face scientifically.
Okay, thank you. And over to HySiLabs.
Okay, so from our side, our seed fundraising was already done with with investment funds, and we are very thankful to them. But for this new Series A, as it's going to allow us to go through to industrial, we'd love to count on all, apart from the financial support, with the industrial expertise. That means either expertise in industrial processes, either expertise in hydrogen. But in any case, we are not only looking for financing, we are also looking for partners. We are looking for those who players in the value chain that need a solution like ours and that would be interested in developing it at industrial scale.
Thank you, Belén. I would like to leave the floor also to our last expert, Alessandro Zampieri from Breakthrough Energy Catalyst, that could provide a vision about support schemes and how the venture funds see this kind of entrepreneurship investments, and what is your vision and how you would like you could support such innovations from your point of view. So please, Alessandro.
Hi, everyone. Thank you, Francesco and Marco, for having me. Very interesting panel. Congratulations, Belén and Carlos and your teams at HySiLabs and LESGO project. Very interesting technologies, essential to enable a hydrogen economy and being able to connect demand and supply by storing and transporting hydrogen in a cost-effective, efficient and safe way. So very interesting panel. I would be, what we do at Breakthrough Energy Catalyst in a few seconds. Basically, we are an investment fund, clean tech. One of our technology of focus is hydrogen, in addition to long duration energy storage, sustainable aviation fuels, and direct air capture. And we look at supporting projects that are early commercial. So projects that are not necessarily in the money because of the green premiums of these technologies today. And we help them with what we call a blended finance approach. So we come in with offtake agreements, with sub-market equity and philanthropic grants to support this project and de-risk them, reach financial closure, close the financing gap, and transition into implementation. Our aim is to actually help scale up and roll out technologies, deploy technologies at a much faster rate than what the solar and wind industry have done maybe 2-3 decades ago, simply because we don't have the time and the luxury of time, to wait so long to see such technologies deployed in the market, which are essential for decarbonization of industries. So that's what we do. Maybe if I may, Belén, first a question to you. You spoke about a demonstration project. I would like to hear more about, if possible, about the size that you have in mind, where you stand in the process, and what's the largest proof of concept that you deployed so far, if you can speak about that.
Sure, no problem. So regarding this demonstrator we are going to have in mid-2022, it's actually a demonstrator at the minimum scalable size to industrialize the process. That means that it will have a non-commercial quantity of production per day, which is around 1 kilogram. Of course, we are not aiming to sell this because that wouldn't make sense, but it would allow us to do all the tests that we need to prove that the molecule is safe, etc. Because, well, of course, as when you have a new molecule in the market, you need to do several tests, etc. And also, it will allow us to integrate the first projects. Of course, we are into collaboration projects today already, but most of them are theoretical. With this demonstrator, we will be able to go practical and to start finally manipulating with our partners the molecule, because the proof of concept we have today is just lab scale in our labs in our headquarters in Aix-en-Provence in France. So the idea would be to at least start improving this also with our European partners, of course.
Thank you, Belén. And what do you expect to be the challenges in the development of this pilot project? And then I would also like to hear more about the timeline to see the next scale project, if you want, so kind of pre-commercial, early commercial scale.
So the main problem that we already face it and we will be facing is the fact that when people don't see the machine, they don't think it's going to work. So as long as we don't have the industrial facility, it will always be very hard to make people aware of the fact that it will work. Even if we have it at large scale, as long as we don't have it at industrial scale, they won't believe in it. And our next step after this would be a more consequent pilot of around 10 tons of the solutions, which is around a ton of hydrogen per year. That will be an industrial, what we could call an industrial pilot. It will be in 2025. And this pilot, of course, will be integrated into the Series S fundraising with the idea of precisely avoiding this problem, because the advantage, let's call it like that, of starting the research in 2018 is that with the demonstrator, all the risks will have already been taken.
Got it. And sorry, I didn't get the scale of the pre-commercial project, the last one that you mentioned, 2025.
So from 1 kilogram to 1 ton.
Per?
From the kilogram to the ton.
From kilogram to ton, Alessandro.
Yeah.
Okay.
Thank you very much, guys. Sorry to interrupt, Alessandro, but the time, as usual, is terrible. So it's as guys from the financial teaches us, the time is stringent, and so we have to go to the next step. And so I would like to thank everybody. I hope that you have seen an example of the program managers try to work, driving the research in the direction of the innovation, speaking about corporates, about strategic, as our colleague Dano said before, about strategic intelligence. And just to give the floor to Marco to conclude, just to say that we are here speaking about hydrogen because we in EIC have got projects funded in hydrogen, so what we call thematic portfolio on hydrogen, and we are starting to evaluate in the next days a call that Marco and me did, a challenge-based call on Pathfinder on green hydrogen production routes. So thank you to everybody. I give the floor to Marco to say the last words. Thank you.
Yes, just to say that we are really on this topic of storage, energy storage, so we are working on other specific challenges on mid-long-term storage, which is very complementary to hydrogen, and also the use of hydrogen combined with carbon to produce renewable fuels, which is another way to maximize the use of this technology. So I thank you for your attendance. Thank you, everybody, and for sure we will go on with this discussion further soon. Thanks.